Welcome to this live webinar on COMSOL presents Multiphysics Modeling of Manufacturing Processes using COMSOL, powered by ITP Media's Manufacturing Today. ITP was founded in 1987 in the UK. The company subsequently relocated to Dubai in United Arab Emirates. Manufacturing Today, India is a leading B2B magazine focusing on the Indian manufacturing sector. The publication covers a wide range of topics, including innovations in manufacturing processes, automation, Industry 4.0, and developments in various subsectors such as automotive or aerospace, tooling, and more. It offers in-depth insights through features, news, interviews, and case studies to help the industry professionals stay updated on the industry trends and the best practices in manufacturing. The magazine serves as a platform for the industry leaders, providing them with opportunities to share their views on the market trends, challenges, and advancements. It plays a crucial role in promoting growth and collaborations within industries within India's rapidly evolving manufacturing industry. For more information, visit the magazine's website at manufacturingtodayindia.com. Now about COMSOL. COMSOL is a global provider of modeling and simulation software used by engineers and scientists in all fields of engineering, manufacturing, and scientific research to simulate designs, devices, and processes. Its COMSOL multiphysics platform product features a consistent user experience across engineering applications. The simulation platform brings fully coupled multiphysics and single physics modeling capabilities, model management, and user-friendly tools for building and maintaining custom simulation apps. The apps can further be compiled into standalone apps via COMSOL compiler. Add-on modules provide specialized functionality for electromagnetics, structural mechanics, acoustics, fluid flow, heat transfer, and chemical engineering. Users who want to interface directly with CAD and other third-party software can do so via the corresponding live link product. Today, we have with us Ashish Uppu, who is the technology specialist at COMSOL, who has specializing in acoustics and structural vibrations. He received his master's degree from IIT Madras in the field of thermal engineering with a focus on fluid mechanics, heat transfer, and CFD modeling, where he was also a gold medalist. His prior experience includes several government and industrial, civil, and architectural projects with a special emphasis on noise mitigation and vibration isolation of structures. Thank you, Ashish, for your time today, and over to you.
Welcome everyone. Welcome to this session on multiphysics modeling of manufacturing process using COMSOL multiphysics. So as I'll be taking you forward for the next couple of minutes on modeling processes using COMSOL multiphysics, specifically focused on manufacturing. So just let me share my screen now. The topic for today is multiphysics modeling of manufacturing process using COMSOL multiphysics. So before starting the session, I would want to briefly cover what exactly multiphysics is and how does COMSOL as a multiphysics tool comes into picture in solving your particular problems. So this is basically the dictionary definition of multiphysics, what Oxford Dictionary has to say with respect to multiphysics. So multiphysics is basically a coupled physics phenomena in computer simulation, or it's the study of multiple interacting physical properties. So the idea here is any particular environment, real environment that you see outside, it consists of a combination of physics phenomena together. And the ability to fully couple these physics phenomena in a virtual environment is what is the role of a multiphysics tool, which happens. So a multiphysics tool is basically, I would say, is a kind of an interface or a platform that brings in real world environment setup into a virtual kind of setting. So to give you a brief example, in terms of manufacturing process itself, if I give you an example, let's say we have a manufacturing process like say welding. Welding is more or less, it's a physical process. If I am planning to bring it in a virtual setting, like in a computer environment. So in case of a computer environment, if I'm trying to set it up, so that's where a simulation tool comes into picture. And when I'm using multiple physics like heat transfer, fluid flow, and other real world physics are coming into picture, that's where the idea of multiphysics comes into picture. So as I told you, so this is what is basically the reason for a multiphysics simulation. So why do we do this? To make highly accurate numerical simulations that closely mimic real world performances. And why exactly do we need this? To make smarter design decisions, to generate new ideas. So whenever you want to actually have a design process in mind, or you have a manufacturing process in mind, you want to implement it rather than making a prototype and experiments which would usually cost you a lot of money. At the same time, you have to spend a lot of time on it. You can use a simulation tool, a very good simulation tool, to reduce the costs for the physical prototyping and experiments, at the same time to speed up your product development and with respect to the multiphysics. So it also helps you, the product also helps you to generate high fidelity models, so in bringing real world phenomena accurately into picture. So before starting, so I'll be going to few manufacturing processes. So the idea here is I wanted to touch upon all the manufacturing processes that COMSOL Multiphysics has used previously, so that you'll get an idea, or you'll get a feel ki what exactly happens in the software, in the tool. So the first manufacturing process that I want to cover was titanium welding. So titanium welding, as most people know, welding, as most people know, is a process of joining two metals together. If you have two dissimilar metals, if I want to attach it together, we use a welding phenomena. Now, titanium welding is a special case of welding process where it's highly unlikely to get experimental results out of it. That's the reason I've chosen this particular model, because titanium itself is a very hard metal. Whenever you're joining those two, the temperatures are very high. So whenever you're trying to measure the temperatures, or you're trying to measure the physical parameters or physical quantities in that particular process or in that particular setup, it becomes highly unlikely or highly impractical to measure them physically, because of, as I said, because of the high temperatures involved. That's when simulation comes into picture. Now, in simulation, again, you can actually go with a normal physics simulation where you can just consider temperature, or you can just consider structural deformation. But in this case, in COMSOL, what we are doing is we are combining everything. As you can see from the current slide to the left side is one of the snippet of the COMSOL session for building titanium welding model. It's basically, I'll be talking more about it in the demo. I'll be showing you a demo of the same particular model, titanium welding model, where I'll be talking more about what exactly each particular option in the list means. But as of now, I want you to just focus on one thing, specifically the last three options, which are not just last three, basically the options just below materials. If you see, there are two options that are available. One is heat transfer in solids, and second is the alpha beta phase transformation. Heat transfer in solids is one physics, and alpha beta phase transformation is second physics. So there are two physics. One is a heat transfer physics involved, and the second one is phase transformation, which is involved. Phase transformation, people who are working in metallurgy would be knowing, is basically what decides your properties of your material. Your material properties is basically defined by the phase composition of your particular material that is involved. And combining these is what multiphysics talks about. So combining these two physics phenomena, which are completely distinct with each other, is what multiphysics talks about. And this is what happens in titanium welding in this particular simulation. So the idea again of ability and the idea of combining these two simulations or these two interfaces together is what helps in making the simulations much more robust, accurate, and highly fiddled. So in this particular example, the alloy plate undergoes heating and cooling during welding, and the process parameter which affect the final phase composition or a phase transformation, the heat affected zone, which you can see from the figure. Behind the title, if you see, there is actually one particular snippet that I've shown, which talks about the heat transfer contours. So the process parameters affecting the final phase composition in the heat effect zone is what is being predicted. So we'll talk more about it in the demo, but as of now, I just wanted you to remember is that final takeaway from this slide is titanium welding or something kind of these kind of welding processes or complex manufacturing process are possible in a multiphysics tool like COMSOL. The next example that I wanted to show you was steel quenching, which is again a common process of attaining softening the metal. So if you softening or hardening the metal depending upon the rate at which you are cooling the metal. So steel quenching or in general quenching is an operation in which you decide the rate of cooling for a heated metal or a heated material to its recrystallization temperature. So the final phase composition is obtained is what decides upon the strength of that particular material. So this is what quenching implies. And the phase transformations during that process of cooling, rate of cooling, is what produces distortion and residual stresses. So this is again a classic example of two physics stitched together. One is the solid mechanics, and second one is the phase transformation. So in this case, it's steel, right? So steel, you have austenite, martensite, bainite, pearlite, and ferrite transformation. So we use that particular phase transformation dynamics along with the structural mechanics to bring in the multiphysics into picture. Now, how do we do that? This is what I'll be explaining in the next slide. But again, here I want you to again remember that using the model builder, you can build a model where you can combine these two effects into picture. So coming to the multiphysics of phase transformation, how does phase transformations, solid mechanics, and heat transfer interact with each other? This is the main idea which I wanted to show, and which this is what happens behind any manufacturing process. What exactly is in the background that happens, or what exactly is running, is what I would be discussing. First thing is phase transformation are dependent upon the temperature. So and the heat, and they produce latent heat, because the better the phase, obviously the melting temperature would change. So because depending upon the phase composition, the melting temperature would change, and obviously the latent heat would change. Between a relation between phase transformation and heat transfer would be the temperatures, because phase transformations are dependent on temperature, and phase transformation and latent heat. So because phase transformation is what is going to determine my latent heat, or the heat at which, or the temperature at which the melting of that particular metal happens. The next one would be phase transformation would produce some transformation strains or the mechanical strains which change in the temperature produced by the thermal strains. What I mean to say is, you have a phase transformation, you have solid mechanics in picture. Now, because of phase transformations, there will be some stresses which will be generated, and also there will be some changes in the during phase transformation. Obviously, there will be change in the temperature. Because of those temperatures, there will be some thermal strains and transformation strains that will be generated. We call these transformation strains are residual strains. So each phase transformation will lead to some residual stresses and strains that will be generated in the material, which is taken care of by the solid mechanics. Now, what is the outcome of these stresses and strains? Your entire shape of your material will change, because obviously the more stress or the more strain the component is experiencing. Like for example, if you have a circle, if I'm applying phase transformation on this, or if this circle is of steel, if the steel is undergoing some transformation from martensite to pearlite or bainite or something like that, the circle would not be circle, because due to temperature and other cases, it could keep changing. So that is the reason why there would be a relationship between the phase transformation and the solid mechanics. Now, how do these combinedly affect the entire setup or the entire model? So the effective material properties, or the effective final material properties, it could be thermal properties, it could be structural properties from solid mechanics, will be a combination of, or will be dependent upon the phase transformation. So amount of phase your material would be having, the difference would be in your thermal conductivity or the temperature properties, heat capacity, and the structural properties like Young's modulus and Poisson's ratio. Final output which this will be giving would be your temperature field, phase composition, and the residual stresses altogether. So this is one thing. So before moving forward, I'll start with the poll question. So I would request the moderators to launch the first poll question. So the idea here is, we want to understand your, basically based on this poll question, we want to understand the audience. We would understand the users, what kind of users are actually attending the session, so that based on that, the next few slides or the next few particular minutes, I'll be tailoring it according to the audience. More than 50% people are new to COMSOL multiphysics. So this is what we've seen. So, right. So I think based on that, I'll focus more on the multiphysics phenomena part, so that it will be much more for people, for the people who are attending it for the first time, who are actually experiencing multiphysics tool for the first time. They would be much more it would be more refreshing to them with respect to what exactly I'll be talking next. So now, whatever I talked until now, so we have something called the multi-metal processing module within the software, which takes care of this, which I have talked about. I'll be talking about in the product portfolio as well. I'll be talking to you about that as well. But the idea here is, metal processing module is what is going to enable you to do whatever I have told until now. Starting from the phase transformations, so either it could be ferrous alloys or titanium alloys, it could be stresses and distortions. So as I told you, it could be thermal strains, it could be the transformation induced plasticity strains or the latent heat. So this is one thing. Apart from that, you can have multiple applications which I have discussed until now. So one is the welding and steel quenching. So apart from that, we have another process called additive manufacturing, which we'll be discussing in the next slide. So additive manufacturing is again another process, another case of multiphysics simulation in manufacturing, where you have, so traditional manufacturing process involves removal of materials. Any material you see, it could be turning operation, it could be welding, or it could be any other particular not welding, it could be either turning operation, it could be machining. Usually what happens is you have a workpiece, you try to remove the material and create the final product out of it. That is one conventional way of machining, because it's much more cheaper that way. The latest one is additive manufacturing, so where you add layers of material layer by layer to create an additive manufacturing process. So that's the main idea behind additive manufacturing. So we have an example which shows how to model an additive manufacturing process which involve few layers of material. In this case, I've taken 3 layers. So 3 layers of material are added to demonstrate to you how the physics works out. So how exactly the physics in the manufacturing process works out. But in general, in realistic scenario, usually the number of layers are actually, it could be hundreds of layers to build that particular material. So but the process and the physics remains the same. So we use something called the activation feature in the solid mechanics interface of COMSOL, which helps you to take care of the addition of materials here. So the current material consists of 3 layers resting on an infinitely rigid substrate. So why exactly I'm taking a rigid substrate? So that my focus would be only on these 3 layers to make that particular specimen. So each layer is modeled by a 3D toroid with a major radius of 1 mm and a cross section and a square cross section of side length 0.2 mm. So as you can see from the additive manufacturing specimen, we have 3 layers. So final product, or finally what we want to get is, we want to determine the temperature distribution of that specimen, because the idea here is whenever I'm adding one layer at a time, the bottom layer would be cooler than the top layer, because initially I add one layer, on top of it I add another layer. So obviously the temperature difference between the bottom and the top layer would be kind of drastic. The top layer would be much more hotter when compared to the bottom layer. Now, because of this heat difference, there would be, the main problem would be the material would undergo distortion. So that's the reason we need to check the temperature variation in the simulation tool, so that the temperature is not overshooting, the material's temperature is not overshooting, so that it doesn't undergo distortion. That's the main idea behind plotting temperature variation, and that's what has been done here. We have plotted the temperature variation to visualize basically which areas of the material are reheating, resulting from the deposition of top layers, which does not result in critical overshooting of the material. So that's the main idea. So because the idea behind any process, manufacturing process, is to retain the shape and get it to as close to the design dimensions as possible, or else there's no point of me manufacturing that with wrong dimensions, right? So that's the reason. The main idea is to first check the temperature, and second is the stresses, which I'll be showing you in the next slide. Temperature to control, to have a check in the thermal strains that are getting induced in the material. So that is one thing. So in this case, left side, if you see, we have the temperature field, which is at t equal to 0.49 seconds. The second part is the temperature versus time, which we have plotted at one particular location, to at each location of your top layer, bottom layer, and the middle layer, to determine to check that, to make sure that the temperatures are not overshooting. That is one thing. The next is basically the stresses. For stresses, the power input from the newly activated material usually generates thermal stresses, which results in the residual stress field in the material at the end of the cooling phase. Now, again, because of which, what happens is your any circular cross section or in that particular cross section would be distorted. So you won't have the same particular shape of the material. It will be usually be distorted. So that's the reason what happens is we go with the simplified model, we try to check the stresses accordingly. So the stress field and deformation at t equal to 470 seconds has been determined in this case, which you can see from the left slide. And to my right, if you can see, there is a variation of von Mises stresses versus the time for the bottom, top, and the top, bottom, and the middle layer. I'll be discussing on one of our case studies from one of our clients. So this is basically an innovation at in an industrial technology research institute. They have developed an additive manufacturing part design. So the idea was engineers at industrial technology research institute, they built a simulation app so which can be used to predict the performance of laser powder bed fusion, which is an additive manufacturing process. Now, why did they go for this? Why not prototype? Because one thing is additive manufacturing, or in general doing experimentation on manufacturing process, is very costly affair, because as you can understand, there are a lot of trial and errors that has to be done. So this trial and error, usually if you're working on a prototype, usually you have to do tons of prototyping, lot of, mostly hundreds of prototyping has to be done, and based on that you have to arrive at a conclusion. So going with the traditional way of, you are developing a physical prototype and working on that and arriving at a conclusion was kind of too costly for them. That's the reason they wanted to move towards simulation. Now again, in simulation they were again stuck with what simulation to go for, because additive manufacturing is more of a multi-physics case, and they wanted to get results which are very close to reality. Product, as you can see, it was example of a injector. If you like, if in the present example, in that image, if you can see, it's the example of an injector. So injector design is something which is very, very complicated. It's not that easy to simulate in a traditional software, and that too when multi-physics is involved. That's when they approached COMSOL Multiphysics, where we helped them to build up an app during the additive manufacturing of a 3D printing, their 3D printing injector. This injector, they used it for the hybrid rocket engine. So the accuracy here was very, very important. To the T, they wanted it to be highly accurate, because this was not going in an automotive, but rather in a aerospace application. So aerospace, obviously, it has to be true, or it had to be accurate 99% of the time. So that's the reason they developed an app to save time and money by assessing the build characteristics for an optimized manufacturing process. And they compared it to the cost of running physical trials, in which using the simulation app reduced the cost by 83.3%. That was one observation, one phenomenal result that COMSOL was able to achieve in terms of bringing their entire final product into simulation platform, so that they were able to fabricate it in a much more efficient and less in a more cost effective fashion. Now coming to the next part. So I think I'll start with the second poll question here. So most people want to understand performance and failure studies. So we have few examples on it. So once we move on to the further slides, I'll be talking more about them. So coming back to next manufacturing process, which is curing. Curing is a chemical process which results in hardening of a polymer material by cross-linking of polymer chains. So where do we use it? For generating polymer materials, or more commonly we call it composite materials, which is again mostly you would see it in most of the automotive and aerospace applications, right? Rather than using metals, people are now using composite materials. The main fabrication is using curing, molding and curing. So these two, they use it interchangeably, combinedly, to fabricate the final composite material. So curing, in rubber terms, we call it vulcanization. So this kind of complicated, it involves a lot of chemical process and complex dynamics that happens in the background for obtaining the final product of hardening of the polymer material by cross-linking. Curing reaction interface has two models. One is the viscosity factor, and second is the reaction models, which are again depending upon, these are standard models which are available in literature. So COMSOL has standard models. So the idea of keeping this was to make sure that, to get to basically tell you that COMSOL has standard models available from literature, which you can use to directly establish your problem. That is one way of doing it. The second way is you can create your own user-defined model. So if you think that there is some something new, like some new model that you have developed from your particular perspective, and you want from your particular research, and you want to implement it in the software, you can use the user-defined function to take it forward. So that is also one special feature that has been provided in COMSOL. In this case, we have used injection molding with curing. So the right side, if you see, there is one option of showing injection molding with curing. So yeah, I wanted to show you a video of how curing works on. So this is basically, the outer side is the mold within which you have the cured material which is falling in. as I told you previously, so we have, apart from curing, we have mold filling, extrusion process, coating flows, and resin flows in composite materials, which uses the polymer flow module, which is again another module similar to metal processing module. We have something called a polymer module to simulate the flow of non-Newtonian fluids, which is again a feature, added feature in COMSOL, which I'll be talking a bit at the end of the slide. So this is one thing that I wanted to highlight. Then we have laser heating. Laser heating involves contactless operations with high heat loads. So the idea is to make them very accurate and fast. One example which I have taken from our library model was laser focused through a semi-transparent medium, depositing heat onto a surface. This is again a very common kind of example in which, or a kind of common machining process where you use laser to remove material or melt down material. Then we have aluminum extrusion, which is again a very common process involved in manufacturing. This model considers steady state condition of a billet flowing through a die. So we have an aluminum billet or aluminum workpiece, which is pushed through a die, which is made of steel. Now, usually it's the die and the workpiece are of large scales. If you see in any plant setting, regular steelworking plant workshop, the die and the billets are of very large magnitude. So modeling these kind of applications usually would be computationally very expensive, because there'll be lot of things to model. At the same time, the dimensions are very large. So when your dimensions become very large, your model becomes very heavy. That's the reason we have an option called symmetry feature. Thanks to symmetry feature, a quarter of the geometry is what can be modeled, has been modeled in this particular application. Because if I model just a quarter, the rest I can actually tell the solver to extrapolate it using symmetry. So that was the main idea behind the symmetry function, which is again a inbuilt feature of COMSOL, which is where I want to actually bring in the idea of submodeling. Submodeling in COMSOL is basically modeling a part of your domain. If you have a very big domain like a cylinder, you can just model quarter of the cylinder. If it is symmetric, you can just model a quarter of it, and then you can actually extrapolate the results accordingly. So that one thing is your accuracy won't be compromised. That is one thing. At the same time, your results will be much more faster, because rather than solving for the entire geometry, solving for part of the geometry will take much lesser time, isn't it? So as I told you, the die material here we used was steel, ASI 610 steel, and the billet material was aluminum. And the analysis that here we have deployed is structural for the billet and the die, then heat transfer for the billet and the die, and the third is non-Newtonian flow for the billet, because here aluminum would be in a semi-solid state. It won't be completely in solid state, because it will be heated to recrystalline temperature, through which and it would be drawn through a die. Idea here is you will be having continuous flow of material, which is again similar to polymer flow, which we talked, right? Polymer flow module. So it will be continuous, like to give you a kind of a relevance or a relatability, I would say, kind of flow of a toothpaste through a toothpaste tube. It would be something like that. So you have a toothpaste, you would have toothpaste flowing through it. So that is the kind of, and obviously the toothpaste here would be very hot, which is aluminum. So it will be that kind of a setting. So coming to some results and discussion, which I wanted to show. So these are the temperature plots, velocity field and streamlines, and equivalent von Mises stresses. So as you can see, the kind of quality that the results usually gets generated because of the output from the solver is something which usually is of research quality standard. This is something which even we, like most of our clients have given us as feedback. So people usually use COMSOL for their results and visualization, because the kind of output it generates, you usually need not need another third party software to kind of fine tune it further. Then I want to finally end the topic with another final concept called the optimization module. So we have something called optimization in COMSOL multiphysics. So COMSOL has features for shape optimization, topology optimization, parameter optimization, and parameter estimation. So I'll just briefly give you an overview perspective of what exactly happens. In shape optimization, you optimize an existing geometry or design. For example, it is held against a certain load. The design is held against a certain load. So you're trying to optimize the shape. For example, in this example that I've taken is the example of a wheel rim, where you are trying to optimize the shape of the wheel. Then we have topology optimization, which can be used to find the optimal material distribution given some constraints. So it's like if you consider a wheel rim, you want to remove some material out of it, you want to create pockets, you want to add material. So that's what topology optimization does. While shape optimization only takes care of the shape of that particular geometry or the domain or the boundary, so of the particular boundary or the geometry, topology optimization focuses more on the entire domain section of it. So that's the main idea behind that's the reason it's called optimal material distribution. Whereas we have another optimization called the parameter optimization, which is quite focused on the determining the optimal dimensions and the operating conditions, and obviously the shape and the position of the geometry as well. So like for example, in this example I've taken, in this slide I've taken the example of a electric motor stator position. So we have a electric rotor in an electric motor with a stator and a rotor. We are considering the rotor part. For the rotor part, I'm determining the rotor speed, and at the same time I'm determining the rotor dimensions, which is the position of the different components constituting the rotor based on a particular objective function and a set of constraints. And the final one is parametric optimization. So parametric optimization is again to find a set of parameters that minimize the discrepancy between model and measurements. Again, this is commonly used for experiment post-processing of experimental data. When you have an experimental data with you, like example in the particular slide which I have taken, we have concentration versus temperature. The concentration versus temperature, the dotted points or the dots are the experimental data, and the line is the simulation data. So as you can see, we have used parameter estimation to determine the closeness or the relatability of the curve with the dotted line. So that's the main idea behind parameter estimation. So this is again, people working in data analysis and post processing, they would be mostly familiar with curve fitting and those kind of applications where parameter estimation comes into picture. And the final use of optimization module, I wanted to end it with a case study. So we have the optimization module or the optimization used for optimizing the factory conditions in at Manufacturing Technology Center, MTC. This was one of the company in Europe. So idea was to make their production much more precise and customizable, and where additive manufacturing calls for new approach to factory operations. So they use a simulation model and app to help factory staff make informed decisions about its operation. So how do they do it? They created the model of the powder bed fusion, as you can see from the images, mimicking the same CFD conditions of CFD and environmental conditions, which would be affecting multiple variables from the weather outside to the number of machines operating in the position of the machine. That's the main idea. So that means what I'm saying is the outside environment as well as the number of machines within the factory. So those were taken into picture, and they added more realistic conditions for it, like the CFD conditions. CFD is basically the computational fluid dynamics part of it, and the model was able to predict how heat and humidity inside a powder bed fusion factory may affect product quality and worker safety. So that was the main idea behind it. So they combined this data with the everyday predictive modeling, day-to-day predictive modeling, to take decisions whether to increase the output, increase the number of machines, increase the number of workers on the shop floor, or to cool the entire shop floor by adding a ventilation system. So these kind of small things what helped them to optimize the factory conditions accordingly. So this ends my presentation on the manufacturing part of it. So before ending, I just wanted to fully cover the COMSOL product portfolio, what exactly COMSOL has to offer for you. So COMSOL Multiphysics, if you see to my left side, we have the base package, which consists of the model builder, where the entire model gets built. We have the application builder, which is used to build simulation apps from models. Simulation app is basically an interface which takes in input and gives you output. So the user, whoever is using the app, he need not build a model or he need not understand simulation as a whole. He just needs to give inputs and you get an output. So it's kind of an input output kind of scenario. So more of a graphic user interface kind of scenario. Apart from that, we have the COMSOL compiler, which compiles simulation apps into executable files, which you can run them freely on any system. And you have the COMSOL server, which is a host and to host and run your simulation apps accordingly. So we have multiple So on top of the base package, we have multiple modules which are available, starting from the electromagnetics module, structural mechanics module, multiphysics module, fluid and heat transfer module, chemical module, and then there is interfacing module. So any particular module or any particular application for any particular problem statement that you want for your particular manufacturing process. Like for example, if you wanted to go for welding, I'll just give you an example of welding. So welding, if I want to model welding, obviously I would require structural mechanics. So I can choose one particular module from structural and acoustics, basically structural mechanics module. I can choose heat transfer module, and accordingly I can stitch it together to build my problem. So that's the main idea. So while purchasing, you can go with the base package along with the modules of your choice, which you can help to build your problem. So that's how COMSOL operates in a modularized fashion. So we have more than 50 plus modules available based on your requirements. So depending upon your problem statement, you can accordingly create your module. That is one thing. Apart from that, we have something called the interfacing products. More than 30 interfacing products are available with us. Interfacing is basically you have establishing COMSOL's communication with a third party software. So what do I mean by that? Just take an example of, suppose you're working on SolidWorks. So you take the interfacing functionality of COMSOL with SolidWorks. So what the interfacing does is it creates a communication between SolidWorks so that whenever you're making designs in SolidWorks, that data automatically gets copied in COMSOL, and whatever the changes you make in SolidWorks automatically gets changed in COMSOL. That's the main idea. That's the main idea behind interfacing. We call it live linking internally. It's a trademark term which we call basically linking between the two softwares. So this is one thing that is COMSOL has in store, which is kind of very different from the other softwares that you find outside the market. The main idea here is to make the process of simulation streamlined and much more efficient, so that it's much more easier for people to make the models much more easier. So that's the main idea behind live linking.
Thank you, Ashish. Thank you for your time, and thank you for giving such an insightful information about COMSOL's products and insightful information about how we can use COMSOL's products into using, staying ahead of the curve. In today's manufacturing world, staying ahead of the curve means leveraging the best tools available. And if you are, and to the audience, if we are looking to reduce cost, enhance product quality, and improve process efficiency, I think whatever Ashish has mentioned is a must. I hope the sessions would have helped you equip with the knowledge to harness the power of multi-physics simulation and help you optimize your manufacturing process from start to finish. Thank you, Ashish, once again, and thank you, COMSOL.